Welcome to qnawire.
Okay, so we have a database problem on some alien planet, and we are ultimately trying to figure out what the acceleration due to gravity is on this planet. Excuse me, by using a box on a string experiment. So let's actually start off by making our table that we'll be using. So it's going to be quite long because there are 6 different data points associated with this experiment. All right. Okay, I think we have enough. So starting off with the force measured in newtons, we have nice 50 Newton intervals. So that's 250 through 500. And then we know the time interval it takes to lift the box up specifically 8 meters. It's 3.3, 2.2, 7, 1.5, 1.3, and then 1.2. And then we are going to calculate the acceleration that's the box feels over each of these intervals. All right, and I made this table way too big, but that's okay. All right, so let me record some more of the information I just said. And specifically, we're working to 3 significant figures. It's 8.00 meters. So the kinematics equation that we're interested in is the one involving the time and the time squared. So that's this one right here. And then another piece of information we're given is that the box always starts from rest. So V naught is going to go to 0. That first term goes away. That makes our life easier. And then let's isolate this equation for acceleration. So that's 2 delta y over t squared. So this is the equation that we're going to be plugging in numbers from column number 2 in order to solve for column number 3. And we'll do that right now. And it's always 8 meters. So if you do that 6 times, I'll give you 1.47, followed by 3.31, 5.54, 711, 9.47, and lastly 11.11. Great. So now we can finally do part A, which is to plot force as a function of acceleration. So hopefully that graph will be big enough. So again, on the y-axis we have force measured in newtons, x-axis acceleration measured in meters per second, and then let's try to get 5 good tick marks on here, and then 6 good tick marks on here. So just taking a look at our data, I think measuring our acceleration in 2's because our maximum value is 11.11 is good. And then having each of our tick marks be 100 newtons is good for the force axis. And just approximately 500 up there. So now we can go ahead and plot our points. So starting with the first one, 1.47 corresponding to 250 will be like around here. 3.31 to 300 is about there. 5.54 to 350 is like there. 711 to 400 is like here. 9.47 to 450 is like there. And then 1111 to 500 is like up here. And then just gonna try our best to draw a straight line through all those data points. Hopefully it goes well. That was terrible. Let's try that again. It's really hard to do with the mouse. Like that. Okay, so it looks a little something like that. I'm sure you could have done a much better job with the pencil. That's part A. Just, building a scatter plot and trying our best to draw a straight line through all those points. And then in part B, we want to calculate the mass of the block based on this graph, as well as the local gravitational acceleration g. All right, so just a general property of lines is that you can find the slope of the line as being the rise over the run. And then in this graph, we can specifically find the mass of the block because our rise, our y-axis is a force, and then our x-axis is an acceleration. So if we divide those through, that will give us units of kilograms left over. So there are more sophisticated ways to do this. If you're interested in getting the errors and involving all 6 data points. But in general, I think just taking the largest data point and then subtracting it from the smallest data point will minimize the error the most, and it gives us a very, very close answer. So I'm just going to take the 6th data point minus the first data point, and then roll with it. So that's 500 minus 250 over 1111 minus 1.47, and that will give us 2 significant figures, a mass of 26 kilograms. And then the last thing we need to do is calculate the gravitational acceleration. So just a little bit more info on the experiment. So remember, we have a block, and then it's of course subject to the gravity of this planet, but we're holding it by a string. And oh, sorry, I'm running out of space here. But we do have a force being applied upward that caused the block to move up 8 meters. So that was the experiment. So if we apply Newton's second law to this block, then we get that the force ma is going to be equal to that applied force minus mg. So in other words, we can solve for g by taking f over m minus a. So that's our expression right here, and then we can just go ahead and start plugging in numbers. For calculating the force due to gravity, you can pick any data point. So I picked one that was close to the center. So I chose the 350 newtons ones using the mass we just calculated, and then the corresponding acceleration, which was 5.54, in order to get a g of 7.9 meters per second.